absent, which I have a few. She's my A student. Okay, we're going to start chapter 4, and chapter 4 is all about applications of derivatives and taking derivatives and finding where the peaks and valleys are. And we're going to start with extreme value functions on closed intervals. An extreme value means that it is the uppermost value in a function or the lowermost value of a function. And then a closed interval means that the domain is restricted. And the reason for restriction is to isolate what we want to assess within that function. Now remember, these are going to be all working functions for you engineers, and for science, it's bugs. The nasty stuff that grows and amplifies. Usually yours are exponential in context. So we're talking a closed interval. Well, the first one we have is the extreme value theorem. This is no different than what we did mechanically to find the tangent lines at zero slope and so forth. But it is the extension of the application aspect of this analysis. So we have a function that is continuous. Number one key problem must be continuous through the entire closed interval, which is why we do that in some respects. AB. Then F contains both an absolute and maximum and called an M and an absolute min, the little m, in the AB. That is, there is some number, x of 1 and x of 2, in that interval where f of x of 1 is m and f of x of 2 is cap m. And all of these contingencies are evaluated, and we'll be using tables here because tables make it a picture for my brain. You do not have to do tables, but for my brain, that's how I see it, okay? And it's not a bad thing. So this particular function has all of the contingencies of what could happen in a closed interval. We always assess the start point and the end point of the intervals in conjunction with the analysis of extrema. So we have an absolute min at the beginning of our domain interval, and then we have an absolute maximum at this point here. Of course, everything else is called local. They're critical in the analysis, but not as poignant as what you're trying to achieve. Is everybody comfortable with that? Everybody comfortable? Okay. So that diagram was great. By the way, that top point is almost a flux, which means it's not differentiable. That means it is a point, but it is flex. It is a guess that would occur. All right. So the first derivative test for local extrema is to set the derivative of the function equal to 0. That means we've achieved somewhere where that changes direction. Is that correct? Change of direction. We can measure pressure, gravity, all kinds of aspects that occur within the function that you're working with. Ours are just platonic. They're just normal functions. And later, as you get into Cal 2, they get more involved and more explicit. Okay, is everybody comfortable with that? Okay, so we have to take baby steps and then get to the real core of what you all will need in your future. Oh, good to see you, Naomi. Naomi, I'll change that missing grade today. Okay, so now what happens next? Now we state all of the x values that occur that create that zero within the function are called critical numbers. They exist as values that define where the function changes direction. And so we introduce critical point. And the book is very interesting because of the elegance of mathematics. It'll say x equals this as f is this, instead of giving an ordered pair of that peak. Does everybody understand that? Because when you do the homework, it'll separate the values, giving you the imprint that you must know the critical numbers before you can estimate change. Am I clear? Questions? All right. So, as expected, this is not going to be a difficult program to do. But I do find that finding extrema, absolute extrema, has a sequence of events. A sequence of events. We have to first find all critical points. That means the endpoints included. Evaluate f of all the critical points and the endpoints. Take the largest and smallest of these values and distinguish them as absolute extrema. Is everybody good? Nothing out of the norm. Small doses of items, because our functions so far have been like to the fourth power, nothing more extreme than that. So now we're getting a little more excited. Some examples of identifying extrema. All right, what do you see? First thing I want you to see that this is what? Yes, it is a restricted, but it is what? This is not a closed domain. So what we have here is our domain of AB. Therefore, the endpoints are not in play. Is everybody comfortable with that? That was this example because we all get our eyes, and mine especially because I'm blind, but we see what we think we see, not what we really see. Okay? What is the worst witness? The one that was there at the accident. About half of the information. And the reasoning is our brain only accommodates what we find the most interesting. Blood everywhere. Okay? Well, what car hit the other car first? Oh, I don't know, but there was blood everywhere. Eyewitness. So, the concept of forcing yourself to visualize what is the change, then we know that we have a critical number at C, right? We have a critical number at C, and absolute max. And I guess we could guess it too. All right. Well, I have another one. Now, in this one, we have a what? Yes. And it's a line. So in this case, it is continuous and it is defined at what is that? -2 and 5. So the endpoint at that is the only one we can consider because it's a line. So what do we have? Okay, again, these examples are to what? Just keeping your perspective, looking for things at clues. All right, so we have this example here. We want to sketch the graph of the following function and determine whether the function has any absolute values on its domain. Explain how your answer is consistent with the extreme value theorem. So we have one complete cycle, right? Now, the cycle of sine is a sideward S, right? Everybody remember that? Okay, now what's the distinction here? What does this sine curve have different? An amplitude of what? 5. An amplitude of 5. So in our consideration of sketching this guy, we're going to do the quadrantals that I care about. 0, for sine, I need pi halves, don't I? What else? Pi. And there you go. We need the quadrantals in order to accurately give a good picture of this sine curve. Now we know that the sine of the radian measure 0 is 0. Pi halves. At pi halves, sine is 1 times the 5 makes it 5. Good, good. At pi, we come back to the ground zero business. At 3 pi halves, where does it go? -5. And then at 2 pi, we have become full circle. So let me see what should be a curvature. Sorry. Okay, does everybody agree? Yes? All right. And now it says, do we have extrema? Yes, we don't even have to do the derivative, right? Because we see it. In our mind's eye, there is nothing better than knowing what the curve says. So our critical numbers are what values? Yes, because that's where the slope is 0, right? Correct? Is everybody comfortable with that? So at these values, we have the min and max, the absolute. Okay, well, we would first have to do our f of 0, which is 0, because that's a critical number. It's a closed interval. Oh, no, it's an open interval. Oh, I don't even have to do those. Sorry about that. It's open. So all I care about is f of pi halves and f of 3 pi halves. Sorry about that. And these are absolute max and absolute min. So if I stated I wanted the derivative, okay, because we did this visually, if I did the derivative of this guy, right? F y prime. Is that right? Oh, cosine. Sorry. Okay, then I would set it equal to 0. sign is 0 at what? Pi halves and 3 pi halves. And we would come up with the same concept that we came with our visualization. Does everybody see that? So is everybody good? All right. Now we have this guy. I thought that was a good problem to demonstrate that your brain works just as well without a derivative as with a derivative. Okay. This one has a polynomial of degree what? Of degree 3. And it's flipped, right? Because the leading coefficient of that 3 makes it not go from the negative, but go from the positive to the negative. And it is on a closed interval. So we have to consider the endpoints. Okay, is everybody clear on that one? All right. So they said determine the absolute values for the function. All right. So our first step is to take a derivative. Negative 6x squared plus 54x minus 84. Really a good little one, right? So we're going to set it equal to, right? All right. So I'm going to divide everything by a negative 6. What is that? If I did 6 is 1, 24, it's 14. All right. Okay. So I have two negatives that add up to 9, and that's 7 and 2. Is that okay? Okay. Now, if they're equal to 0, each factor equal to 0 will cause a 0 to happen. These two numbers lie within the domain. So my critical numbers are 1, 2, 7, and 8. Is that clear? Those are my critical numbers. Okay, now I'm going to use my calculator because I will mess up on this math. Okay, is everybody good? All right. A minute. There it is. Okay, because I'm going to want, it's still turning on. There it is. Okay. All right. What I want is going to be f of 1, 2, f of 7, and f of 8. So I'm going to clear whatever I have there. to my y equals and clear what I have there and enter my original function, making sure I put a negative. Taking my time. You know I'm terrible. All right, so I've entered my function. I'm going to double check that I put a negative in the 27 and the giant 84. I'm going to go to second graph and I'm going to enter my values. Always in front. And I'm going to have a negative 59, negative 76, a positive 49, and a positive 32. All right. From this, we know that this is a absolute and an absolute. Oh, I misspelled that up there. Sorry. Maximum. And these are local extreme. All right. Well, if we have this and we know the parameter of what we're looking at, we can structure our graph window. In other words, this is y min and this is a y max. So, and we know our domain is 1 and 3. So let's see what this graph looks like, because I always want you to be able to look at what we have. I'm going to make my domain 0 and 9, one more than what I need. And my y min, I'm going to round to negative 80, 50. And it, let's do 5s. And there it is. Almost looks like a sine curve, doesn't it? Is everybody comfortable with that? Everybody good? Did everybody get the same answer on your calculators? Make sure. Okay. This is a different look, and we know an absolute value cannot have a negative inside the radicand. And we have a closed interval, sorry, of negative 1 and 2. You know, it's some kind of arc with a start point and infinity, but it's closed within the negative 1 and 2. So in this case, they want the absolute maximum and minimum values. All right. So our first step is to take a derivative. I'm going to rewrite it first. And it's flipped. Oh, it's flipped too. All right. And we've got a chain rule going on in this one. G prime of x is going to be a negative 1/2 of the argument to the 1/2 minus 1, a negative 1/2, then the chain rule of the negative x squared. Is everybody okay with that? Did I do good chain rule? Okay, I got a knot. Okay, I'm going to multiply the negative 1/2 with the negative 2 and get 1, a positive. That will be an x. Now I'm going to turn this to the square root of 4 minus x squared in the denominator. Did I upset anyone? I upset anyone? Right. So now we're going to set f prime of x equal to 0 for critical numbers. We already know 2 of them. What are the first 2 we know? Yes. So we're going to see if there's something in between. And according to the rule, that's supposed to happen. I don't know. So I'm going to have x is 0. Does everybody agree? If I cross multiply the square root times 0, I'm going to get 0. And that's because the denominator cannot be 0 as well. So we have our critical numbers. I should have used set notation on the previous one. I apologize for that. So now I'm going to use my calculator. Because I need the g of negative 1, the g of 0, and the g of 2. Here we go. Go to my y equals. I'm going to clear that mess. And I'm going to put my original, which was the square root of, let me look where I put it. Oh, there it is. Okay. Oh, and it's negative. Oh, I'm so sorry. Did I leave that off? Let me look. Oh, I did, but it doesn't matter because it's, even if it's negative x, if I divide by negative 1, it's still 0. But I got to be exact with you guys because you'll go back and she said, oh, she dropped it. Oh, that's right, we did. Thank you for that. I thought maybe I did a math error, and I'm pretty prone to that. Thank you for that. I appreciate it. So for my critical numbers, I'm doing a negative 1, a 0, and a 2. So this is a negative 1 and 732. It really is more than that because if I put it over there, it is an irrational number, but it's close enough for that. And then I have a negative 2 and a. So what do I have? Evaluative. Well, this is the absolute min, isn't it? And this is the absolute max. All right, now we want to see what that looks like. And since we've got the parameters, so I'm going to go to my window, and it said negative 1 to 2. So, I better make it -2 so we can see better, more better. And we have negative, I'm going to do a -3. And, um, oh, and I won. Everybody good? Questions? Anything difficult? No, not really. Okay, now here we have a mess because we have e, which is an irrational base, on top of an exponential, on top of a polynomial product. Normal, ugly structure is what we have. So we know we have a closed interval. At -1 and 6. And we have a product rule and X and chain rule. So let's see what we can do. So we're going to, we're going to take a derivative. Bam. So I have g of x equals 4x to the third e to the -x. So my g prime of x is going to be, and I'm going to do my variable first because that's easy, 12x squared e to the -x. Plus, now I'm doing e to the -x, so that's 4x to the third to the -x, and the chain rule makes it a -1. Does everybody see that? Everybody get g prime of x equals that 12x squared e to the -x, and this is going to be a -4x to the third e to the -x. All right. So we're going to set 0 equals 12x squared e to the -x minus 4x to the third e to the -x. Now, folks, if there's two ways of seeing this, I can factor out an e to the -x, and when I make it to the 0, well, that times 0 is 0. No? All right, let's just do it. Okay, here we go. So I'm going to have the 4x to the third e to the -x equal to 12x squared e to the -x. Is that okay with everybody? If I divide by e to the -x, it just becomes 1, doesn't it? That's what I was getting at, but it's all right. It's all good. Because we would have put it in its natural form and multiplied by 0, and it would have been gone. So we're still going. So I'm going to have 4x to the third equal to 12x squared. Correct? All right. All right. So right here, I'm going to divide by 4 and divide by x squared. Is everybody good with that? There's 3 lie in our domain. Yes. Did I do good math? Check my math. Like it? Okay. It's pretty decent. Okay. We're good. Now that we have are critical numbers. Therefore, I'm sorry?
You could set x equal to 0 as well.
I could set x equal to, oh, yes, absolutely. I left that off because I divided by the e.
How did you 3 didn't win?
What happened to,
You didn't win it.
oh, well, then you didn't have that as a critical number. First. Why I always ask you. Now, where did the zero happen? Was because I factored out the e to negative x. All right, guys, and both of those lie within that domain. So now I have my critical numbers. They all lie in that closed domain. So I'm going to have g prime of -1, g prime of, oh, I'm sorry, not prime, just g, of 0, g of 3, and g of 6. Okay, and I'm not going to do any math, so we're going to put it in the calculator. That way I don't totally embarrass myself. For x to the third, second e to the negative x. All right. Or x to the third, e to the negative. Great. Now I'm going to go to my second table. I have the -1 already there, the 0, the 3, and the 6. 3, 6. And our values are, of course, these are all irrational numbers that you're looking at, but I'm putting what showed to 3 decimals at least. All right, so what do we have? It looks like this is an absolute max. Do you think that's true? Looks like an absolute min. All right, well, let's test it out. Let's do our window. We know our window was -1 to 6. Our y min is like -11 and 6, because we said it was 5. And look at there. On the money. Okay. Everybody good? Okay, class. This is my last example for this group. One only wants the critical numbers. Not want anything more than that. And it's not, and it is an open function. So what would be our range? If got a cubic, and so we're going to have a negative infinity to infinity to consider. So that's why the critical numbers are only the ones we seek in the center. Is everybody comfortable with that? All right. So here we go. I'm going to factor out, well, I'm going to go ahead and put 0. 6x. So what do I have? Yes? I have nods, so I must be correct. So they're both local values, the twists and turns within that cubic. Is everybody comfortable with that? Let's take a short break because I have to load up the next one. I was tutoring this morning, so I didn't load it. Is everybody okay? So everybody take a break for a little bit.